the threshold and above the threshold values, consider 0 and 1 as the two stable states of the transistor, and obviously the computer's components are made out of these transistors. Okay, so we have got various circuits, combinational circuits like adders and multiplexers and decoders and stuff, which get a series of inputs and give us an output, a particular type of an output. So we've seen one decoder like the one we have seen in case of the 7-bit display. We've seen that, and adder is one combinational logic. Why are these called combinational logic? Because these logic circuits, they give an output as a result of the uh, inputs that are put in at that point of time. There are other circuits which we have not done. We are not going to do it this week. We're going to do it next week. These are the latches and the registers, which are the sequential circuits. They basically give an output with a view to or as a result of the series of states they are in, and they're called sequential circuits because their output is a result of the sequence of inputs and outputs that have happened so far, a sequence of the states, and so those are called sequential logic or sequential logic circuits, and those are used as memory elements. Now you see, computers, whatever we do, we have to store values and we have to use those values. Now you see, when we are storing the values, where we are storing it, we are storing it in memory, and the memory is actually made out of transistors. As I said, transistors can operate on a 0 and 1 basis. Okay, the threshold value and below threshold value, which we generally consider as 0 and 1. So we do that. So now that is why we represent everything, all alphanumeric values are actually represented in terms of numbers. Numbers, specifically binary numbers. Why? Because no other number will actually be able to be, no other numbers will actually be able to be represented properly. Because if you talk about a decimal number, for example, on paper we use a decimal number system. So we use a decimal number system. If you use a decimal number system in a computer, that means you have to have at least in each of the element which can hold a digit. It's just like a bit is a binary digit, a decimal digit is just a digit. So if you have one element holding all these holding a one digit, then you have to have 0 to 9 0 to 9 voltage levels. See, having 0 to 9 combinations is easy, but in one element, just one element, having 0 to 9 levels of signals, that's a bit of a tough ask. Why? Because you're using transistors. They operate in a very low voltage range, and voltages can easily fluctuate. Zero isn't exactly zero, it can be 0 point something, or maybe even 1 or 2. 5 volts isn't exactly 5 volts, it can be 4 point something or 5 point something. It's a very, so there is a fluctuation there. Now if you're talking about a transistor, that is, I'm just talking about the normal build. There are lots of different types of, in fact, in Jadavpur University, they have um, in Jadavpur University, they have a uh, research going on. I think still there, I don't know, but they have a very strong foundation in research about analog computers and stuff. I'm just talking about the normal digital computers that we use. So in the normal digital computers, these transistors can only hold like a 0 or 1 value. So having 9 different voltage levels, so 9 different levels of values, is too much. So basically, that is exactly why we go for a binary sequence. Either it's a binary or a multiple of that. Like for example, if we have an octal sequence, which is like 8 digits, that can easily be represented using 3 bits. One octal bit can be represented using 3 bits, as you know. Then hexadecimal sequence, which we normally use a hexadecimal sequence. So this hexadecimal sequence, we have 4 bits being able to represent one hexadecimal bit, or correspondingly 4 bits can be compressed to a one hexadecimal digit. So we use this 2, 8 or 16 basis. Generally we use a 2 or a 16 basis number sort of system, so that we can work well with our computers, or we can work at ease with our computers, with the circuits that the computers are built out with, that helps us with that. So we have done some binary arithmetic. We have seen how to add, multiply, divide, etc. We have seen how the number system progresses. We have seen some just to make sure about the number systems, just to make sure about so that you can understand the number systems properly. Just to make sure of that, I have given you a few examples regarding different other number systems. I've used base 15, for example. So that's what we did at first, the number systems bit. The videos are available, and in fact the last 2 videos have actually been doing so, that they are being put up now. I mean, they'll be put up in 1 or 2 days. I haven't been able to do that, so I'll do that, and so you can have a look at that. And the other thing obviously is, next what we did was to look at the digital logic gates: AND gates, OR gate, NOT gates, XOR gates, XNOR gates, and so on and so forth. So you know all of that. So what I had you do is, so there are two universal gates, which are the NAND gates and the NOR gates. So in the NAND gates and the NOR gates, so what did we do? We Why are they called universal gates, by the way? Why are NAND gates and NOR gates called universal gates? So the NAND gates and NOR gates are called universal gates because you can form any gates you can form. You can form either NAND. I mean, you can form any gates using either NAND or NOR. You don't need any other gates. Right? So let's say you want to form an AND. You can do that using NAND NOR. You can, if you want to form an OR, you can do that using NAND and NOR. If you want to form a NAND, that is just a NAND gate. A NOR you can form using non NAND. If you use a NOR gate, then that's just a NOR gate. But if you want to use a NAND gate, you can use it using NOR. So like that. So any number of gates, or rather any gate, the gates that we have, any of those gates can be formed using a NAND or a NOR gate. Now you may ask, sir, in that case, if we have we already have an AND gate, you can already have a OR gate, you can have a NOT gate. So in that case, why do we need to find out whether a NOR gate can form an AND gate or not? The answer is very simple. You see, these gates, they are made, or they're fabricated as an IC. So there is an AND gate IC, there is a NAND gate IC, there is a NOR gate IC, there is a NOT gate IC, there is an OR gate IC, like XOR gate IC, like that. Now you see, when you are constructing a computer, just imagine you're constructing a digital computer using these transistor circuits. So what will happen? When you're constructing these, you have to use different types of these ICs for the AND gate, for the OR gate, for the NOT gate, etc. You have to use these different types of ICs. On the other hand, if you use just a NAND gate, you can use one IC type, any number of those. You can use one IC type and you can form all the gates. Say if only the NAND gates are available to you, you can form all the gates. If only the NOR gates are available to you, you can form all the gates. So that is the simplicity of, except the fact that obviously, if you're trying to form a different gate using a NAND gate and a NOR gate, the circuit becomes a bit complex. That's very certain. For making a NAND gate, for making an AND gate out of a NOR gate, you need 3 NOR gates, like for example. So basically, the circuit complexity increases. The circuit complexity increases because you have to form a different gate using a different gate. That is exactly why circuit complexity increases. That'll give you that. But if you do not have other gates available, or if it is in some way, when you are manufacturing a computer, if it is in some way not very conducive for you to get a uh, not very conducive for you to get a anything other than a just one gate, then you go for either a NAND or a NOR, because with NAND and NOR you can form any of those gates. So that's the beauty of it. So that is why we explore the ideas of forming different other circuits using NAND gate or NOR gate, which I asked you to practice because that will be a part of the assignments I'll give to tomorrow. Now, we also did floating point representation. You might, number representation inside a computer happens because of the. So we looked at the number representation. It happens because of the number of bits that are there. So the combination of bits that are there are taken. For example, if you have a 4-bit, or if you have an 8-bit memory, so each of the memory latches have each of the memory registers have eight. Okay, eight sort of eight sort of flip-flops. Each of those flip-flops can have a 0 or a 1, and thus you have a 0 or 1 in each of those units. Now each memory unit is 8 bits, which is 1 byte, and each byte, how many numbers can they actually have? Well, they can have one number per combination. So obviously, because it's a latch, it's a register, it's a latch. So or rather, it's not exactly a latch, it is a clock latch. So basically it's a bit more it's got signals and stuff coming, so it is as we'll do later on in next week we'll do it. So it is a bit more complex than a latch. It's not just a simple latch, it's a register. So in that register, obviously you take the entire register together. You normally do not consider one single flip-flop. You actually consider the entire register. So we take the entire combination into account. So how are the combinations coming up? We have 8 flip-flops, so we have 8 zeros to 8 ones. These are the total number of combinations, and each of those representing a number. Now if you have only if you have only unsigned numbers, that is 0 and 1 positive, then you have 8 zeros to 8 ones totally representing 0 and positive numbers. So all zeros are obviously 0, and then 7 zeros and 1 is 1, 6 zeros 1 0 is 2. Like this it goes on. But you have all these combinations for 0 and positive, and actually comes up to 255. As you can know, 2 to the power of 8 minus 1. However, on the other hand, if you are trying to also incorporate negative numbers, so it's a bit complicated. How will you represent it? How will you represent negative numbers? You've only got 256 combinations. So the answer is very simple here also. 128 combinations kept for negative, 128 combinations kept for positive, and that includes 0 and positive. So if you keep 128 combinations for negative, you have minus 1 to minus 128. And if you have uh, 128 combinations left for positive, then you have 0 and then 1 to 127. So that's total 128 values. This is 0. You've got 0 and then 1 to 127. That's 127. So 127 plus 0, that is total 8 combinations, total 128 combinations, not 8, 128 combinations. So that's why you have minus 1 to minus 127, minus 1 to minus 128, and then 0 and then 1 to 127. Like this also you can work out the 16-bit. If you have for example, if you are doing a dev C++ or a turbo C++ on DOS, you have normally have you're doing C, then you have a 16-bit integer. So you can easily in that case work out. In fact, I've worked it out in case of the class itself. You can simply work out. So the 2 to the power of 16 of those, half of those 2 to the power 16 divided by 2 belongs to minus 1 to the least negative number, and half of those, that is 0, and that is 2 to the power of 16 by 2 again belongs to 0, and 1 to basically 2 to the power of 16 by 2 minus 1, that is the range. And this is what I've done. And then uh, I also, so, and how are these numbers arranged, by the way? The numbers are arranged in such a way they are forming a 2's complement format. Once again, what is a 2's complement? So a 2's complement is basically, just we have 10's complement in case of binary numbers, we have 2's complement there. So it's just the opposite. So for example, if you are taking the operation 5 minus 4, so this 5 minus 4 requires a subtractor. But if you want to decrease the type of circuits you want to use in your computer, so that you want to have it simplified, then you want to do it maybe using an addition. So how can you do a subtraction using an addition? Well, simply because 5 minus 4 is nothing but 5 plus minus 4. 5 plus minus 4. So if you have a representation of 5 in binary, and if you have a representation of minus 4 in binary, and you add those two, you have 5 minus 4. Once again, minus 5 minus 4. If you have a representation of minus 5 in binary, and you have a representation of minus 4 in binary, and you add those two, you have minus 9. Because immediately the circuit will know that we have two similar signed numbers. So the magnitude, the absolute magnitude will increase, and the sign follows from the sign that is there. So it's a very simple way. So by using adders only, just by using adders, we can do any type of addition and subtraction. How about multiplication and division? Well, multiplication is repetitive addition, and division is repetitive subtraction. So that's how it is. Now, um, we also did uh, floating point representation. Now you see, integers are pretty easy. Okay, so signs. How are signs related? The signs are related this way, that when you are representing them on the byte, the last, that is the we. So if you're writing from this, you can imagine. So this is my left, this is my right, this is my left, this is my right. Now you can imagine what is the convention. On the right hand side of me, that is on the left hand side of the number, right hand side of me, left hand side of the number, we have the smaller digits. Like for example, if you're writing 19, which is the uh, least significant digit? 9. What is the most significant digit? 1. Why is it called least and most significant? Because 9 is a units place, 1 is in the tens place. That is why magnitude is more. So an error will produce a bigger error than in the units place. So that is why it's called a most significant digit. Similarly, in bit also, most significant bit, least significant bit. If you consider this to be my left and this to be my right, we write the number like this from left to right. So the first, that is the units place, will be this. Then twos place will be this, like this will go. So basically the least significant digit will be to the right, and most significant digit will be to the left, and this is how conventionally it is written also. It is termed that these, if you have a 16-bit number, it is termed as D0 to D15. D0 is the first bit and D15 is the last bit. So the last bit is generally reserved for the sign. So if it's just 0, it's a positive one. If it's a 1, it's a negative one. But it is all open to interpretation. If we are using a non-sign, that is an unsigned number, that is all zeros and positives, then even the one range of numbers will also be positive. On the other hand, sorry, if we are using a signed representation of numbers, then in that case all the zero range numbers are positive and 0, And on the one and range numbers, except 1 and all zeros, that is comes out to be invalid. But other numbers, the one range numbers, are all uh, they're all negative numbers, and they're arranged in such a way that it looks like a circular sort of field. Just as the number system is there, it looks like a circular sort of field. And this is all to do with the representation, and they come out as a two's complement, so that we can just use the corresponding number when we're using addition and stuff. So as you can see, these are arranged like this. Then you can see, if you're using the index 0 1 2 3 minus 1 minus 2 minus 3. So similarly here, it is arranged as 0 1 2 3 like this, up to the highest zero range number, that is the highest positive number. Then we have 1 and all zeros. Then it goes on. Representation is done in such a way that the nearest number to the least positive number is the most negative number. The nearest number to the most second most negative number is the second least positive number. The third least with the third most. The fourth least with the fourth most, like that. So basically, the arrangement is like a circle. So we have, if you take a number here, the corresponding one according to that, the corresponding one on the circle will be its negative representation. 1 minus 1, 2 minus 2, like that. And out of these n bits, d0 to dn, okay, so actually this is n plus 1 bits, and this n bits represent this d0 to dn minus 1. These dn bits represent the number's magnitude. This represents the sign. The total n plus 1 bits, n bits for the, so if you have a 16-bit number, we'll have 15 bits, n equal to 15. That's for the magnitude, and this 1 for the sign. Except if this becomes an unsigned number, then the total n plus 1 bits will be a number. So in case of an unsigned representation, all of these will be valid numbers, and all will be 0 and positive numbers, culminating in 16 ones, which is 65,000 something. I think 65,536 or something like that. Okay. This is what we did. Now that's integer representation. Now we also did. So look at this 2's complement addition, for example. Right? 5 minus 3 is 2. Okay. So you take 5 and you take the representation of minus 3. You don't do minus 3. You actually take minus 3 representation and add these two together. There is one carry bit because it's we know that it's 2's complement representation. So the corresponding this for that will be 2. It's an easy way of changing it, actually, that basically uh, when we have the when we are changing from normal bits, that is the normal positive representation, not normal. There is nothing called normal or abnormal. The positive representation to the negative representation in 2's complement. What we do is we take it from left to right, and when we reach the first one, we change all the bits after that. For example, so 5 minus 3. So 3 is 1 1. 3 is 1 1, as you can imagine. 3 is 1 1. With a 4-bit representation, it is 0 0 1 1. We change to 2's complement. How do we do that? First one is encountered, it is written. Next one is encountered. Because the first one has already been encountered, we make it a 0 and the other two become 1. This is minus 3. This is 3, this is minus 3. And this obviously is in the 4 bits that you have. This will be the 5th bit which have to be discarded. This will be 2. So like that you go on. As you can see all this. 5 plus 4, 5 plus 3, minus 5 plus 3. So you take the 2's complement of minus 5, add to it 3, and what you get is minus 2. You can see this is how do you change that? Imagine that after you receive, so 0 0, so this is 2, 0 0 1 0. Once you receive 1, all of this is changed. Minus 2, 2. See, you have to ignore this one because it's a 4-bit number. This is 2. This one, the one that has been marked, is minus 2. See the similarity? Once you encountered the 1, 0 change to 1. So this is minus 2. So this is the glory of 2's complement addition. And as usual, you may imagine that we are always trying to do these kind of things, invent these kind of tricks, because we want to minimize the circuits, we want to minimize the operations. Because you see, we have to implement those at the hardware level, and so it becomes a bit of a problem. So it becomes a bit of a problem. Now we did. Now you see that's integer, but then in that case you may ask, so what is character? Simple, they're integers also. But then in that case, they're not considered as numbers; they're considered as alphabets. They are called they are considered as integers representing alphabets, so that none of the and what is the difference? Difference is in operation. What is what is a number? Arithmetic works on that. Arithmetic sort of plus minus division etc. work on that. What is an alphabet? Arithmetic operations do not work on those. You can see if they're equal. You can see what sign it is. You can add. You can just concatenate. There is no addition. For example, a plus b, you can have it as ab. There is nothing called a plus b as such, unless and until those are variables. In that case, that is a numeric operation like that. But what about floating points? So floating points represented like this. We take out two different parts. Sign bit. This is the magnitude, exponent of the magnitude, and this is the decimal point. In this case, the binary point, but it will be represented as the decimal point. Once again, sign, magnitude, power. For example, if you have minus 0.25, okay, minus 0.25 is actually not minus 1.25, it is minus 0.25. Minus 0.25 on the negative side, you are having 1/4. So this is minus 1/4. So that is why you have a representation like this. With integers representing sign, integers representing magnitude, integers representing the power of the magnitude in power of 10, integers representing the point decimal point sign, integers representing the magnitude of the decimal point and the power of 10. Now, this would be say for example 2.5 multiplied by 10 to the power of minus 1. Let's go to the left, not the right. So 2.5 10 to the power of minus 1, and this sign would be minus, for example. This is how we represent floating points. about number representations. Now we also did the adders and okay um, decoders. Now those obviously are I put the videos up for those the adders and the decoders. I think if you have you all subscribed to my channel, YouTube channel? Okay, in that case you will have received the last ones. So the decoder and the 8-bit, you all received that, isn't it? Okay, so I'm not going to go into that again, but that's what we did after that. So the adders and the parallel adders and adders basically add 2 bits. We're talking about full adders, adding 2 bit and getting the carry out. So there are parallel adders where lots of different adders are used to add all the bits of two numbers parallelly. It is fast, but it requires a lot of space. But a little more complex, but requires less space, is a serial adder, which takes. Okay, let me just show one second. So this is your adder. Okay, these are the signals, inputs A, B, C, and the carry. The carry is given as 0 at the first. Because as you know, any number, say if you have 2 plus 2, that is 0 plus 2 plus 2, that is 0. Now if you have 12 plus 15, that's 5 and 7, that's 0 plus 2 plus 5 is 7, then 0 plus 1 plus 1 is 2, like that. First of all, the carry is given as 0, and then whatever the carry is, that will be circulated. These two are connected with these using the formula, and these are odd out using the formula. The sum of the two bits are given by nth bit plus n bit of A plus n bit of B plus the multiplied by the carry. Sorry, not A and not B and C, not A and B and not C, not A and not B and not C, not A and A and B and C, like that. So these are the two, and for the this is Cn plus 1. Why? Because for the sum n, the carry is going to the next bit. So for the sum n, the carry is going to the next bit, that is on the left. So that is why that's Cn plus 1. That is given by A naught B C, A B naught C, A B C naught, and A B C. And so this is how we have A, B, and C, and these are not A, not B, and not C, and we connect it with these circuits with ANDings. There are AND operations. There are seven of these are needed, obviously, because this is common, A, B, and C. So these are needed. We connect them as usual. This is for the A bar B or B bar C. This is for A bar B C bar. Like that, this is A B bar C bar, A B C, A bar B C, A B bar C, A B C bar. We connect it as per the formula, and we OR it. Outcomes from the first OR we got sum, next OR we got carry. And so these adders are there to add the two bits. When you have as we can see that numbers are represented using many other bits. I mean, we have a 16-bit representation, for example. So 16 bits need to be added. When adding two numbers, say we are having two 15-bit numbers, we add them to we produce a 16-bit number. Two 16-bit numbers will produce a 17-bit number, like that. So how can we do that? We have these parallel adders. These are adding the two bits, adding the two numbers bit by bit. or rather, each of the bits are each of the bits are dedicated one adder and a carry. Carry first goes in as 0, and then like it goes on. It's fast, but it's expensive to manufacture because you need a lot of these adders, but it's very fast. If you are, and it requires a bit of space, expensive not in just terms of cost, but also in terms of memory space. And if you want something more smaller than that, go for a serial ladder. In serial ladder, we use something called a register. Register is basically a latch of flip flops. Just like you have the addend, that is the number to which it is added, and this is augment, okay, which is augmented to addend. So you have the bits A1 to A15, and then the bits B1 to B15. They're taking in the book. Okay. So they're taking in the book 15-bit numbers. So we have A1 to A15 and B1 to B15. Now this will be added in parallel. This will be added in parallel. In serial, this is drawn in. This is drawn in. The carry is 0. So carry flip flop is 0. This is added. The sum goes into S1. The position is shifted to the left, which is now empty and will be containing the next sum. And the carry from this is recycled into the carry flip flop. So when it comes to that point of A2 and B2, A2 is fed in, B2 is fed in, and C that is coming from A1 plus B1 will also be fed in. Sum will go into S2. The carry will go into the carry flip flop as C3. Like this goes on. This is a serial adder, full serial adder. The point is, what we can achieve here, we can achieve we can use it using a very small amount of space and just one adder. Also, but the point is, you have to remember that the operation becomes more complicated. You see, the operation obviously becomes more complicated because you have to take this, add it, keep it here, shift this, take this, add it, keep it here, shift this, like this. And needless to mention that this actually is a bit more time consuming because of the additional operations that goes on there. Okay. So this is an example, matter is an example of a combinational circuit. Another one that we saw is the 8-segment display. Okay, this is the display in which we use a, okay, decoder like this. Okay, a 7-segment display decoder, and these are the combinations and these are the outputs. Each of the outputs are connected to one arm of the display. So there are 7 arms of the display like this. Okay, A, B, C, D, E, F, G. Each of them having a 0 will be turned off, having a 1 will be turned on, and that is how from 0 to 9 we can make. This is 0, this is 1, this is 2, okay, this is 3, this is 4, like this it goes on. And this is given by, so we have this decoder, we get these outputs. These are all the valid outputs that will form the physical appearance of 0 to 9, and the others do not have any, these are errors or invalid. Why invalid? Because these will not form the physical representation of 0 to 9s. But if you have, say for example, also if you include alphabets, then that may work that way. But alphabets are normally very poorly represented using. For example, this is a B, this is a G, but then how about an E? For E, you have to have this kind of an E. An A will have to be this. Okay. So you have to mix and match small letters and capital letters for this. But in that case, many other signals will be valid. And this is also a combinational logic because It depends totally upon the output give. Sorry, rather the input given at that time. The input given at that time will determine the outputs. Unlike you see, unlike the registers here, if you look at the sum register, for example, why is it not a combinational circuit? Because the result of the sum register will be the result of all these operations and the status that it is going through. So first of all, it is all zeros and a one, then it becomes all zeros and something, then something, then something, then something. At the end, whatever we have at the end will be the sum. Now this is not a direct this is not a direct result of the input just at that time. No, it is a result of the summation, and this is what we are latching on in the register. So whether it is containing the result of all the states that we have been through. So this is why it's called a sequential circuit, which we will actually cover in the coming week, not this week, because as I said, that many of our friends have gone for uh, exams, and it will be very unfair for us to discuss any new topics. That's what it is. So this is what we've done so far.